Today, I'm going to be talking about single photon frequency conversion for frequency multiplexed quantum networks in the telecom band. Me, along with my colleagues, Robert and Ben, and my supervisor, Mirko, been working on this project since last year. So, come on, you can work. There we go. So just to start out, I'll give a bit of an overview about what I'll be talking about today. So obviously, I'll be talking about quantum frequency conversion across the telecom spectrum. I'll talk a little bit about why you would want to do such a thing, namely for enabling quantum repeater networks. Then I'll talk a little bit about the platform that we use to do our frequency conversion. Those are our waveguides in lithium niobate. And then I'll go into a bit of details about the frequency conversion itself and how you would do it across a telecom wavelength division multiplexing spectrum. Then the next section, I'll talk about the protocol that we came up with to do our frequency conversion. It's our two-pump frequency conversion scheme, and I'll talk about how to balance it all up and deal with the phase matching to make it all efficient. As well, I'll talk about some of the challenges inherent with the protocol, and I'll talk about the results of our classical experiment. Then finally, I'll talk about the conversion of single photons, namely our conversion experiment to observe Hong-Ou-Mandel interference. I'll talk about some of the challenges that we had in sorting out that experiment, as well as the results, and anything that we might need to deal with for any future implementation of this protocol. So, to start out, this work is all to do with helping to enable quantum communication. So, quantum communication can be used for secure communication by quantum cryptography, but it's constrained, unfortunately, by how far you can send the photons without losing them, namely the propagation loss. The thing that makes quantum cryptography secure, the no cloning theorem, is a bit of a double-edged sword, because even though you can't copy the quantum information, it also means you can't classically amplify it to boost a signal. That's why there's a big push in using telecom technology. So the telecom C-band is a set of wavelengths balanced around, centered around 1550 nanometers, where the propagation loss through an optical fiber is really, really low. It's as low as 0.18 dBs per kilometer, and that's good. Conveniently, telecom technology already forms the basis of our classical communication. So that means there's a whole lot of optical fiber already buried in the ground, waiting to be used for our nefarious purposes. And it's also comparatively quite cheap. That's why there's also been a big push in the quantum realm to use telecom. We've got good telecom detectors now that the SNSPDs, they can detect, they can work with better than 95% efficiency, and we're getting better, brighter, higher purity single photon sources in telecom all the time. Now, even though that 0.18 dBs per kilometer is quite good, it could be better. What it translates to is that only after 16 kilometers of fiber, half of your signal is already gone. In order to boost that distance out, you need to use something called a quantum repeater network. That's shown schematically below here. A quantum repeater network consists of all of these separate nodes. Those are these W-shaped looking things in the bottom that consist of single photon sources, quantum memories, and some measurement equipment. They work by two entangled photon sources generating photon pairs. One photon from each pair is stored by the memories, and the others are subjected to a joint Bell state measurement. The result of that measurement then conditioning the entanglement of the two memories to one another. then you're allowed to retrieve the photons from those memories and send them down a fiber link to another Bell state measurement in the middle. And conditional on the success of that experiment, you will entangle memories from separate nodes. And then on, you can do subsequent measurements until you've got entanglement across quite a long distance. The important ingredient in the quantum repeater network is, of course, the quantum memory. Now, the quantum memories that have been studied extensively are unfortunately typically not compatible with Telecom. The ones based on rubidium, they operate at a wavelength around 780 nanometers, and in optical fiber, this translates to half of your signal being lost in only about 600 meters. Other materials, including praseodymium, they're resonant around 600 nanometers in the visible spectrum, and their propagation losses through fiber are even worse. That's why there's been a push to work with Telecom compatible quantum memories. These memories are based on materials like erbium, and even the group of Matt Sellers in CQC2T has been working on one of these erbium-based quantum memories. Recently as well, there's been a memory based on a microfabricated optomechanical resonator. It's been fabricated specifically to be resonant within the Telecom band. Now, these quantum memories are getting better. Matt Seller's group has shown that they can have quite a long coherence time with their memories. The disadvantage with these memories, as well as basically all other memories, is they're quite narrow bandwidth. This plot here shows the absorption spectrum for erbium in a crystal, an erbium doped crystal. This whole feature is maybe only 3 gigahertz wide, and these absorption peaks are only megahertz wide. That's not ideal when you want to deal with the Telecom spectrum, because there's a whole 7 terahertz available for you to deal with. It would be good if these narrowband memories could have access to the entire WDM spectrum. That would allow useful things like massive multiplexing of your quantum signals for either speed or as a means of distribution. And that's what we want to try and enable with our frequency conversion protocol. So the thing that we have at our disposal in order to achieve this frequency conversion are our waveguides in lithium niobate, our reverse proton exchange waveguides in lithium niobate. This style of waveguide has shown low loss. We can fabricate them with low loss, and previous experiments with them have shown that you can get near unit efficiency, near unit conversion efficiency. And also we can fabricate them with periodic polling. That is where you can periodically invert the ferroelectric domain of the crystal in order to support phase matching, which I will talk about now. So what kind of conversion can you achieve with the periodically polled lithium niobate? So the 2 kinds of frequency conversion we can do are called sum frequency generation or difference frequency generation. Put simply, that's where you can get the frequency of a signal, combine it with a bright pump, and then the frequency of the signal and the pump together generate a signal, a target at the new frequency. Also with difference frequency generation, you'll start with a higher frequency signal, mix it with a lower frequency pump, and the difference between signal frequency and pump frequency will generate your target frequency. Now this frequency conversion proceeds following this rather simple looking differential equation. The amplitude of the target increases or changes according to a coupling strength that's determined by the the waveguide geometry, the material used, the lithium niobate, namely. Also, it involves the signal's amplitude and the amplitude of the pump. And you've also got this inconvenient phasor here at the end, reducing the efficiency with this phase mismatch term. Now, this comes about because of the difference in phase velocities between all of the different frequencies involved. But thankfully, it can be cancelled out using our periodic poling. We choose our poling period so that it follows this formula and can cancel out effectively cancel out the phase mismatch with a small penalty to the efficiency. So what we need in order to achieve our frequency conversion across the telecom spectrum is high efficiency. Our waveguides can do that. Preferably, we want a bit of tunability. This is where we start running into problems. That's not really something we can do easily with our waveguides, because you would need to tune the periodic poling, and that's not something you can do on the fly. And also, you would need to make fairly small conversions on the scale of a few hundred gigahertz. In order to do that, you would need a pump of a few hundred gigahertz. That's microwaves or distant infrared. Good luck coupling those into a waveguide or even generating them. So it's a bit of a problem, right? So we might as well look at what other people have done in different platforms in order to achieve some frequency conversion. So first off, there's adiabatic frequency conversion. So that's where you can send your signal into a silicon, either photonic crystal waveguide or a resonator, and shift the frequency by subjecting it to a bright optical pulse that will cause a time varying change in the refractive index. It's a bit of a complicated ballet of getting all of your pulses right and getting your photons all properly confined into the right spaces at the right times in order to do it efficiently. It's a bit of a pain. So the other way of doing it, the more familiar way, the better studied way of doing it, is by 4-wave mixing. That's done using, it can be done in any material, but it's usually done in long optical fibers. And it's done simply by, with 2 pumps, where the sum of pump 1 and your signal is equal to the sum of pump 2 and your target. And it's a simple way of shifting the frequency that way. It also has to deal with phase matching restrictions, but because all of the wavelengths involved are quite similar to each other, this restriction is quite relaxed. The phase mismatches are very, very small. But also it is way less efficient than what you can achieve in the periodically poled lithium niobate. So it's the right kind of thing, it's the right kind of frequency conversion, but not ideal. So our goal is to try and emulate this 4-wave mixing using our lithium niobate waveguides. And conveniently, that is something we can do by a process called cascading. This is simply a fancy way of saying that you perform the sum frequency generation step and a difference frequency generation step at the same time. It's done by having your signal, mixing it with a bright pump, and it will generate an intermediate frequency that I'm calling SFG. And then at the same time, you've got a second pump, which is generating a difference frequency from that intermediate frequency into your desired target. It's got the high efficiency of the lithium niobate waveguides, and also you've got the tunability simply by changing your pump slightly, and it can make the small frequency conversions necessary to get it across the WDM spectrum. Now you've got two phase mismatches involved, though, because there are two different processes going on. In order to make this process as efficient as possible, you're able to phase match for the average phase mismatch between the two different processes. And you set that in as your periodic polling, and the process can proceed efficiently. This leaves a small phase mismatch difference that provides the limit to efficiency, but it's the same limit as in the four-wave mixing in fiber case. It's small and easily dealt with. So here's a quick schematic on how the conversion proceeds as the light goes through the waveguide. You start out with a whole bunch of signal. It will deplete as you continue through the waveguide. At the same time, your intermediate frequency grows. And while that's happening, it's also being brought down into your target frequency until the end. And this little deficit, the little bit left over in the SFG mode, a little bit left unconverted from the target mode, is due to the small difference in phase mismatch delta K. Otherwise, the conversion proceeds according to these coupled differential equations. Fairly simple. There's the coupling strength, there's the pump power, signal converts to SFG, SFG converts down to target. Simple. So we, of course, wanted to demonstrate this process. So we did an experiment just to show how the protocol works. We start out with some bright pumps, and we can combine them together using a WDM. We also have a signal, which we'll combine on a beam splitter, and then just pump straight into a waveguide. Primarily, we want to find out what kind of efficiency we can achieve with our waveguides. So whatever comes out of the waveguides will hit this splitter and be picked up by these power meters. We also want to quantify some possible noise effects that might happen because of our protocol. So we had some of the light being sent into this optical spectrum analyzer as well. And of course, we got some results for our experiment. Solving our coupled equations, doing a bit of maths, we got out a formula for the conversion efficiency of our protocol. And we wanted to see that it matched quite nicely with our conversion data, and thankfully it did. We also figured out what kind of maximum conversions you can look at for particular waveguide geometries, namely the length of the waveguide and the small phase mismatch. This Q term here is just a function of the total pump power involved. But that's not quite the end of the story with this. This maximum conversion that you can achieve is limited by a function of the small phase mismatch and the length of the waveguide, meaning that technically longer waveguides will actually give you a lower maximum conversion efficiency, even though they can result in higher conversion efficiencies for lower pump powers. But that's not the entire story for the maximum efficiency. So just doing a bit of an illustration of what happens to the conversion as you keep increasing the amount of pump power. You'll first reach a maximum efficiency, but then the process will reverse itself and continue on in this periodic kind of fashion as you keep increasing the power. What the maximum efficiency actually looks like is that it involves this integer term m, meaning that the maximum efficiency quoted on the previous page is just when m equals 0. Otherwise, you've got a peak for each integer m. This bottom plot is what it looks like when your delta K, your small phase mismatch, gets a little bit worse than ideal. Your maximum efficiency first drops, but you can technically keep ramping up the power higher and higher, and your efficiency will, over time, get better and better. But unfortunately, it's not that simple. There are a couple of problems with the protocol that kind of prevent you from just putting in infinite power. We're doing three-wave mixing, but to begin with, we're inputting three-wave. We've got our two pumps and our signal. This means that our problem is a little bit over-defined. What this results in is that we can get unexpected interactions between our pumps and our signals, and it can do things like cause some losses from the protocol or generate some extra noise that we don't want. The first thing that can happen is that our signal can interact with the wrong pump to begin with. So instead of interacting with pump 1, the signal can interact with pump 2. It'll generate this new intermediate frequency, and then pump 1 will bring it back down into this new target frequency that is not our desired target frequency. And with more and more power, this can happen in kind of a cascade, on and on, off to the left and off to the right. What can also happen is that the pumps themselves can generate either some frequency of their own or their own second harmonics, which can then go on to generate noise either by SPDC, the spontaneous generation of photons, or you can get some DFG effects going on with your signals and targets. It can pull power, it can cause extra noise to be placed on top of your signal and target frequencies. We quantified this in our experiment. We got some traces from our spectrum analyzer, and these peaks show the noise peaks due to our some frequency generation between the pumps and any cascades that come off that, as well as the extra unwanted peaks that are loss coming out of our desired signal and target cycle. But all is not lost. Those things are relatively easy to fix. Thankfully, all of these processes are not well phase matched with the waveguide and its periodic polling. This means that due to the effect of the phase mismatch and the length of the waveguide having a detrimental effect on the conversion efficiency, it also has a detrimental effect on these noise processes as well, meaning that you can go a long way to eliminating them by having a longer chip requiring lesser pump in order to achieve your conversion. Something else we discovered from some numerical exploration of the protocol was that you don't need to use pumps that are nearby your signals and targets to achieve efficient conversion. You can, in lithium niobate waveguides, you can actually use pumps that are near to 2.4 microns rather than 1550 nanometers in order to still achieve efficient frequency conversion. On top of that, that basically eliminates any noise that you generate from any SFG or some second harmonic generation from the pumps because they're even further out of phase matching with the periodic polling. So let's move on to the quantum experiment. So extending this protocol out into the quantum domain is fairly simple. Following the formulation from these guys, Kumar and McKinstry, in a separate paper, we can construct a Hamiltonian for the quantum frequency conversion process. if we can treat the pump frequency as, the pumps involved in the process as classical fields, which is a reasonable estimate to make, seeing as they are so much larger than so much larger in amplitude than the signals involved, we can treat the signal and the intermediate and the target frequencies as quantum modes and construct the Hamiltonian following this, where we've got a coupling strength and the pump powers and some operators, some creation and annihilation operators for the signal, target, and SFG modes, where in one step the annihilation of a signal photon means the generation of an SFG photon, and at the same time the annihilation of an SFG photon means the creation of a target photon. And to complete the Hamiltonian, of course, we need the Hermitian conjugate of these processes, and we've also got these terms that describe our small phase mismatch, now delta K. From this Hamiltonian, we can get a set of Heisenberg equations of motion for the system. We can solve them, and we can reach what is hopefully a familiar looking conversion efficiency for the process. And our maximum conversion is the same for this process as well. Just like the classical case, it might be handy to take a quick look at what other people have done so far in quantum frequency conversion, things that they have been using them for. First off, you can use a single stage of some frequency generation in order to interface a telecom signal with a rubidium memory. That's simply put a signal photon in, use a bright pump, it'll generate it to a rubidium memory frequency. Another thing that's been done, this time in the 4-wave mixing case with an optical fiber, was use frequency conversion for improving the heralding efficiency of a single photon source. You'll start out with a heralded single photon source, generating single photons. The herald will tell you which pumps to turn on for the process, and then the pumps together will bring all of those photons down to a common frequency at the end. So you've got pure heralded photons at a single frequency. And also, the frequency conversion process has been used to demonstrate a Hong-Ou-Mandel interference between photons of different frequencies. In this case, it was done using the frequency conversion itself as a beam splitter between a telecom photon and a photon at 775. But that's something similar to what we want to achieve, but we don't want to use the frequency conversion process itself as a beam splitter. We just want to be able to use a regular old beam splitter. So our experiment was to also demonstrate this Hong-Ou-Mandel interference. For the people watching who are not quantum optics people, Hong-Ou-Mandel interference is the kind of standard demonstration that people use in order to show that they've got interference between genuine single photons and not something like thermal states or just dim coherent light. The way the Hong-Ou-Mandel effect works is that first off, 2 photons will enter a beam splitter. If those photons are distinguishable from one another, meaning that they're slightly different either in frequency or difference in arrival time or maybe a difference in spatial mode, those photons will act independently of each other, and they will each have a 50-50 shot of either leaving the beam splitter separately from one another or leaving the beam splitter together. But what happens if those photons are completely indistinguishable from each other is that those photons will always leave the beam splitter together. They'll either go all go left or they'll all go right. The way we can detect this happening is by placing detectors at the outputs of the beam splitter and watching for coincidences. That's when both detectors go off at the same time. As your photons go towards indistinguishability, usually in arrival time, you will see a reduction in the number of coincidences between your detectors. What you're ideally looking for when you've got single photons is a reduction in coincidences below the limit of 50%. This 50% limit is due to the absolute limit in reduction that you can see when you're dealing with either coherent light or thermal light and not single photons. So our quantum experiment, we wanted to observe this Hong-Ou-Mandel interference between photons that have initially started out to be distinguishable in frequency from one another. And then we wanted to use our frequency conversion process in order to make them indistinguishable in frequency, and then observe this Hong-Ou-Mandel interference with a reduction in coincidences using a single photon detector. So to start out, we put some pulses, optical pulses, into one of our lithium niobate waveguides and generated photon pairs by SPDC. Then we separated them out using a wavelength division multiplexing module. One of these photons goes to a delay stage that we can use in order to delay the time of arrival of the photons at the beam splitter, while the other photon was sent to our conversion waveguide. At the same time, it was mixed with our two bright classical pumps that are combined together, amplified, filtered out to hopefully get rid of any noise from our amplifier, and then mixed on a beam splitter, favoring the single photons 97:3. So following the conversion, the photons are sent on to another filtering stage, and then they are combined on a beam splitter with the delayed photons. And then hopefully after that, we can observe our Hong-Ou-Mandel interference using our avalanche photodetectors and a time delay counter. First off, a couple of challenges that we met with our experiment. We had a lot of noise, so much noise. A lot of my time was spent trying to either mitigate or avoid this noise. There are a couple of sources of noise that can come from the experiment. First off, it could be coming from the amplifier used to amplify our classical pump signals, but I ruled that out with some extra filtering of our amplified classical light, so that wasn't a big deal. Another source is cascaded SPDC. That's where our bright pumps inside our conversion waveguide are generating some frequency generation between themselves, and then that some frequency generation is spontaneously generating photon pairs, which then coincidentally fall on top of our signal photons frequency. But that was also not likely because there was very little of this some frequency generation being generated in the waveguide. It was just very poorly phase matched. The next most likely thing is Raman noise coming from the waveguide. This is something unavoidable when you're dealing with lots of power in a waveguide. Sometimes it's a thermal process that will sometimes generate some photons away from the bright pump lights that you're using, and inconveniently they can fall on top of your signal frequency. The way you fix this is with some spectral filtering. I tried to do that as tightly as possible with some good old-fashioned overkill. First, I've got a triple pass through a 50 dB filter, so that's 150 dBs of filtering right there, plus a diffraction grating in order to tighten up the frequency bin of our photons and hopefully eliminate more noise that way. Another thing that we tried to do was reduce the detection windows of our detectors. Since the single photons are coming in on a fairly short pulse, ideally it would be good to only have the detectors open during that short pulse. But unfortunately, our detectors have a comparatively broad window, which unfortunately let in a lot more noise. Something else we could try was to change where we had our pumps. We can do a little bit of limited tuning of our periodic polling by tuning the temperature of our chip. This allowed us to move where we had the bright classical pumps in order to try and put them in a low noise place. But unfortunately, everywhere was kind of bright noise. This is the spectrum of the noise that I measured coming from the waveguide. And I already had the pump sitting in probably the optimal position to reduce the noise. Even after all of these measures, our noise was still quite high, still 6 times brighter than the actual signal photons that we were measuring. Another thing that we tried to do to kind of improve our signal was to improve the overlap in frequency between our converted photon and our delayed photon. And we got quite a good spectral overlap of 96%. So finally, here are the results. The good news, we got quite a high conversion efficiency, 55%. So that's very, very good. Following that, we've got the classical visibility of our beam splitter was quite high as well. Not ideal, but quite high, 97%, and our spectral overlap, 96%. So that should only be reducing the visibility of our Hong-Ou-Mandel interference by a little bit. But our big problem was still the noise. There's this massive noise floor in our Hom dip. Not accounting for this noise, we got a raw visibility of 49.3%, which is just shy of the 50% visibility. But because the noise is everywhere, we can take it into account and subtract it away. And following that, we got a fairly good visibility of 84.5%. So that is above the 50% limit for the Hong-Ou-Mandel interference, to show that we've got single photons and that our conversion process maintains those single photons. So a couple of changes to deal with for future implementations. The first thing we can do is we can fix the Raman noise. It is not something that is inherent to this protocol. The first thing we can do is we can move the pumps further and further away from our signals. Like I showed you before, we can, in the lithium niobate, use pumps near 2.4 microns. This will have the dual effect of reducing the Raman noise by moving the pumps further and further away, as well as by reducing any potential noise from the cascaded SPDC by making that pump self-SFG process very, very inefficient. The next thing you can do to improve it is to improve temporal gating. If you've got detectors that have a much shorter dead time than ours did, or detectors that you can gate to a very, very short window, that will kill a lot of your noise as well. Another thing to do, if you want to do exactly the same experiment, would be to herald on 4 photon SPDC events. It will mean that your detection rate will go way, way down, but the purity of your results will go way, way up, because you're selecting on heralded results only. Another thing to try in the future to reduce the Raman noise would be to explore using, rather than bright continuous wave pumps for the conversion, we could use pulsed pumps. Since the Raman noise is dependent on the average power of the pumps. If you have, while the conversion efficiency is dependent on the peak power of the pumps, if you have short pulses for the pumps with a high peak power, they also have a very low average power, so that will reduce the amount of noise again. And finally, another thing to try is different chip platforms. So this protocol doesn't just work in our proton exchange lithium niobate waveguides. It'll also work in titanium diffused waveguides. It'll also work in etched or ridge waveguides. It'll even work in other Kai2 materials like periodically poled KTP if you can put waveguides into it. So those are things to explore for the future. And as well, this process, this Raman noise might not even be a problem with the quantum memory if this protocol is used in conjunction with a quantum memory. The quantum memory itself can be used as kind of a spectral or temporal filter because they only interact on such a short bandwidth, and they can be used as a temporal filter using the storage and retrieval pulses of the memories. If you have the conversion pumps turned off during state retrieval and detection of the photons from the memory, then you don't have any more of this Raman noise. So just to conclude, we have a protocol for converting photons across the telecom spectrum. This protocol takes advantage of the high efficiency frequency conversion using periodically poled lithium niobate waveguides, and it's much higher efficiency compared to the equivalent 4-wave mixing process in an optical fiber. We understand what kind of advantages and drawbacks this protocol has, and we have ways to mitigate them. Unfortunately, this particular implementation of the protocol was a bit noisy, but we know how to solve that problem, and it may not even be an issue at all in the future. Okay, thank you for listening, guys.